So we received, Matt Ike and I are co-PIs on that. Matt Ike is in crop and soil environmental science and is a soil chemist. And let's see. So we received a one-year grant, roughly $45,000. And the formal title is The Physiochemical Effects of Temperature and Water Chemistry on Stream Degradation. So the problem is, whenever you urbanize an area and you change the hydrology, so basically you go to, say, fields or forests, which are porous, spongy, absorb lots of rainwater, and you pave it, as Susan has talked about, a lot more water runs off. Okay? And what we see is what is called the urban stream syndrome. And so this is a picture in Roanoke, Virginia, and you can bet that that pipe probably wasn't installed in the middle of the channel. Okay, so this is a stream that is this big, but yet the channel is now this large. So that's a big problem for a bridge, pipelines, any type of infrastructure crossing the stream. It's land loss, okay, if you own land adjacent to the stream. And then also the question is, where does all that sediment go? So it becomes water pollution. So we start talking about issues of pollutants. Okay, there are a lot of contaminants, metals, pesticides, bacteria that are attached to sediment and get transported. It fills up reservoirs. It increases drinking water treatment costs. And then there are all the ecological implications of both the channel degradation and the sediment pollution. Okay, and so our main paradigm in urban streams is it's the flow that's causing this. You put more water down the channel, it moves at a greater velocity, and it causes erosion. Well, that's true, but we're missing part of that, and that is when you have cohesive soils, which are very fine grained, the particles are so small that surface chemistry becomes important. Okay? And so the question is, in prior research, we've noted that erosion rates increase with increasing water temperature. Okay? And this makes sense if the strength of the soil is a surface chemistry effect. As you increase temperature, you're going to start to spread those molecules farther apart. Okay? So that makes sense. And so another one of my questions was, well, what about other factors? So pH, salt content, anything that affects the surface chemistry that's going on. So the hypothesis is basically that not only is it flow that is increasing channel degradation in urban streams, it's also the changes that we see in water chemistry. And so what we did was, so we have two clays that we're looking at, 3 temperatures, 2 pHs, and then looking at basically road salt, sodium chloride, at 2 different concentrations. So coming out of the tap, it's about 5 milligrams per liter. What we notice in streams is up to 5 grams per liter in the winter. Yeah, lots of salt. Okay. And so what we did, I didn't finish. This is the large flume that's in ICAS2 with marked stuff. And so what we did was we created soil cores, okay, and tried to make them as uniform as possible. There's a lot of variability in any erosion type of research, so a lot of work goes into just trying to reduce the variability to what you're trying to test. And so we have these soil cores. The clays that we're looking at are the ones that are most common in riparian areas or streamside soils, which would be montmorillonites and vermiculites. These are younger soils. Okay? And so we created an artificial wall. I think the next slide shows this. Okay, so what we did first is a preliminary study, because nobody's done this quite like we have. So most people put the soil sample in the bottom of the channel because you have better control over your boundary shear stress. We said, well, that's not a stream bank, and gravity is helping you rather than working against you, so we put the cores in the side. We also wanted to eliminate a lot of variability, and so one thing we found is that moisture content has to be very tightly controlled, and the time that the soils in between when the cores are made and when they're tested has to be, that's a very tight tolerance there. Because the longer the soil sits, the more it tends to consolidate. So that affects our variability. But anyway, preliminary study, a master's student completed. She actually tested 3 different soils. She also tested kaolinite, which is a very common soil in the southeast. And she found that the average erosion rate increased by a factor of 2, changing from water temperatures of 12 degrees Celsius to 20 degrees Celsius. Now, this type of temperature change has already been observed in urban streams due to summer thunderstorms. Okay, so if you've got a summer thunderstorm that dumps over an urban area, not only are you getting a huge flush of water, but it's also superheated. Okay, because a parking lot is an awesome heat exchanger, right? Okay. We also saw an average with vermiculite of 3.5 times. Okay, so these are huge increases in erosion rates between 20 and 27 degrees Celsius. We're also looking at, are there simple tests that we can make of the soils to be able to predict what type of erosion rates we're going to get. Zeta potential measures your surface charge. Okay, so we were looking for correlation. We found some, but we didn't have a lot of data. We saw no correlation between the applied stress and the erosion rate, which is very different. Okay, usually that's how you predict erosion is with the boundary shear stress. We saw no correlation. Okay, so that's suggesting that it's all chemistry driven. Okay. We used a lot of this preliminary data, and Cully and I are co-PIs with a postdoc who's now finishing up the project. So we submitted to geomorphology and land use dynamics. Hopefully we'll hear soon. Another thing we found was placing the soil cores in the wall showed aspects that nobody else has seen before. So changing that methodology has made a big difference. So right now we're finishing up the complete study. We adjusted some of our methods based on the preliminary study to try and get better resolution in our data. And we're just about done. The postdoc, Siavash Shamir, is currently at CSDMS, which is an NSF-sponsored program, Community Systems Modeling Dynamics or something like that. Because what ultimately we like to do is develop a model that we can make available to this program and have it up on the web where people have access to it and can insert it into their own programs. Let's see. Multi-steps, there's a student right now with the multi-steps program who's looking at using impulse instead of boundary shear stress as a better predictor of erosion. He's just about done with that. So there have been linkages to some of the other programs on campus. I anticipate, actually I've got a proposal about halfway done that will also lead into instrument development. Running this in the flume and having to change the temperature and chemistry of 1,000 liters of water is a real pain in the butt. I mean, it really limits how much you can do. And so my goal is to develop new instrumentation that will use a lot less water and allow us to change the conditions, which increases the number of reps we can make. So, and we're seeing huge increases with the salt. The pH not as much, and temperature is just blowing the soil away. It's amazing. This is far more than I ever expected. So the implications of this are huge for stormwater management. Okay, so highlights, we've shown there's a huge increase with temperature. Guess what? Stormwater management practices don't treat for temperature. If anything, they make it worse. Okay, because you hold the water in a pond and you expose it to sunlight, right? Great. Okay. Zeta potential has some possibilities as being used as a predictor of the susceptibility of soils to this type of erosion. And this could really rock EPA's world. If this means that we suddenly have to start thinking about temperature as a pollutant in urban stormwater to maintain stream bank stability. Right now we look at only flows. Temperature is not even considered. Let's see. So we have had a master's thesis. Siavash presented a poster at AGU in December, and we are working on a peer-reviewed manuscript. Oh, and actually the presentation at AGU is leading to a collaboration with